Okay, so the idea with this activity is you are going to be working with your partner to construct a confidence interval. So it's going to lead us through doing a few things. What we want to do is we want to estimate the proportion of kisses that land on their base using confidence intervals. So what's going to happen? You are going to take a sample of size 50. You're not taking 50 Hershey Kisses, okay? I'm not rich. These things are expensive. You're going to have a sample of size 5, and what you're going to do is you're going to drop them, and you're going to look at what proportion land on their base. So in this case, 1 out of the 5 landed on its base. What is that as a sample proportion? 0.2, right? 1 out of 5. So you're going to do 10 different trials to get a sample of size 50. Sound good? Okay. Okay, so we should have all of these numbers that we added up, and I don't know what you got. Maybe we got 17. So then I walked around and I saw some people write p hat as 17. That doesn't make sense. Proportion is between 0 and 1. So we should have taken that 17 and divide by 50 to give us 0.34. That's just an example. Yours is probably different. I saw one group with 17, but most of you probably do not have 17. Front group, what did you get for p hat?
17.
Out of 50, but
0.34.
Yeah.
Okay, what did you guys get? 0.26. 0.34.
0.44.
0.27. Ooh, okay, so the highest I heard was 0.48. The lowest, I don't know. There's a 0.27 in there. So many of us got different answers. Why do you think that is? Why would we have different values of p hat? There's a few different reasons. One is a stats reason. One is just your own kind of personal reason. Augie, thank you. Okay, the big one, sampling variability. Right? Even though you all have kisses from the same bag, there's just going to be variability in the ones that I gave you. Do you think they're all identical? Probably not. Did you notice that you all didn't drop them the same way too? Some people dropped from really high, some people dropped from down low, some people did this with their hand, where some people just open their hand up. Maybe that has something to do with it. I'm going to say the dropping method. Okay, this next part, are the requirements met? We're just going to skip that. We'll talk about that in the notes. What I want to do is I want to get to the actual calculation part of this. Okay, so you all should have a formula sheet. Last class, we talked about the way that you construct a confidence interval is you take your point estimate plus or minus a margin of error. So that is the general idea. Point estimate, you've already found. Point estimate is your p hat. What we need to do now is we need to calculate the margin of error. This is why I have us with the formula sheets. I want you all to look at the front of the formula sheet, the front yellow page. So do it with the person next to you. The second to last line on the bottom, if you can look at this, it says confidence interval. And then you should notice it gives you a formula in words, though. Do you see that? Statistic plus or minus. You guys with me? Okay. So on the formula sheet, it says statistic plus or minus critical value times the standard error of the statistic. So all we need to be able to do is figure out what does the critical value mean, what does the standard error mean. Statistic is just that p hat. Okay, so if we are focusing on just the margin of error part right now, I will tell you critical value for proportion is always z. And I will show you how to find that in a minute. So critical value is always Z. You flip to the back of the yellow page. How convenient is this? You're going to notice a column that says standard error of the statistic. So all you have to do is figure out which case are we looking at. We are looking at the case of one proportion, the very first line. So that standard error is the square root of p hat 1 minus p hat all over n. Okay, so this stuff in blue is our margin of error. P hat you already found. It's whatever your p hat is from above. N is 50. Z is what we need to find. Z comes from the normal curve, and it is related to what percentage of our confidence interval we want. So in this case, we want 95%. Here's how you're going to find that. If you look at this first table, it is the standard normal table. We're not going to use that table. Look at the second table. So you are looking for table B. Table B. Table B. Look at the top until you see table B. It should say T distribution critical values. Do we see that? You with me? We're all on table B? Okay, so initially we should be thinking, well, that is not Z, that's T. Okay, so along the side here, left side, you should see degrees of freedom with a whole bunch of numbers. The very last line, do you see has an infinity? That infinity means Z. So if you look at the bottom of the table, it says confidence level. So you'll go to whatever the confidence level is that you want, in our case 95%, and it is the number right above that. That is the Z. So hopefully we see that that Z is 1.96. Is that what you got on your table? Yes? Okay, take a minute then to calculate the margin of error. The margin of error is that 1.96 multiplied by the square root stuff. Okay, I didn't do the calculation, but I at least saw one group that had 0.1358, so I'm just going to say hopefully that's the right one. Okay, so last thing that we are doing with our partner is you are now going to construct that confidence interval. So what you are now doing is you're taking whatever your p hat is, you're going to add and subtract that margin of error, which will give you an interval with two values. So what I want you to do right now is I want you to construct that confidence interval, so find both sides of the interval, and write a sentence interpreting that interval. So I didn't come up with an interval, but this is the wording that we used for interpreting. We are 95% confident that the interval blank to blank contains the population proportion or true proportion of Hershey kisses that land flat on their base. Okay with that? Michaela?
Wait, so for the interpretation, it's either like the true population proportion or just the true proportion?
Yeah, either you can say population proportion or true proportion, but something has to be in front of proportion. I didn't tell us this last class because I didn't want to scare us. But one thing that College Board is very, very picky on is the tense that you use. Yeah, it's crazy. If you use past tense, so if you said landed, you would not get credit. It is crazy. I understand why, but I don't like it. So you cannot use past tense. I will point out from now on when you use past tense, I'm not going to take off for it, but it's something that you need to be aware of. Present tense or future, not past. What I would suggest you do is just copy the wording directly from the question. That's what I did. Hershey kisses that land flat. I would just copy it right from the question because then you're not going to get in trouble. It's ridiculous, I know, but that's how it is. Okay. Okay with that part? Here's the last thing we're going to do, is we are going to compare our confidence intervals. So I'm actually going to have you guys come up here and draw on my iPad. What you're going to do is you're going to put a dot at your point estimate, so whatever your p hat is, and then you are going to estimate your interval on either side. Okay, I want us to notice a few different things. First thing we should notice is there are a lot of different point estimates, right, since we all took our own samples. Other thing is, besides the fact that these are not the most accurate, particularly, I won't happen there. The margin of errors are different. Why is that? Why do we have different margin of errors? Why are some of the intervals wider and some are narrower? Alex?
So we had different sample proportions?
We had different p hats, right? They all had the same z, they all had the same n, but we had different p hats. If we took bigger samples, like a sample of size 100 versus 50, that sample of size 100, are we going to have a wider interval or a narrower interval? Narrower. If we took a higher confidence level, like 98% instead, if we were more confident, wider or narrower? Wider. More confident, we'll get wider. Okay, do you think every single interval captured the true value? What percentage of them should, theoretically? 95%. Any guess as to what the true value actually is?
3.8.
It's not a possibility because it's between 0 and 1. Do you mean 0.38? Okay, 0.38. Point 0.3 is the true value. So at least according to Hershey's. According to Hershey's, 30% of the kisses should land on their lips.
How did you figure that out? Like, did they know that?
Good old Hershey's came out and told us. Okay, let's think real life though. Real life, how many intervals are you actually constructing? 1. Real life, you have 1 sample, 1 interval, that's it. So you might have been lucky and gotten an interval like this that captured 0.3, or you might have been unlucky due to sampling variability and gotten an interval like this that didn't capture the true value. You have no way of knowing. How do we feel about constructing confidence intervals? We feel good? Okay, we're going to skip around on these notes a bit, but we're going to start out with an example. Students in an AP Stats class want to estimate the proportion of students at their school that own a graphing calculator. To do this, they surveyed a random sample of 102 students. Overall, 57 of the 102 students they surveyed own a graphing calculator. Construct and interpret a 95% confidence interval for the true proportion of all students at the school that own a graphing calculator. Okay, first thing, since we already did 95%, we're now going to do 90% just to be different. Yeah. It says construct and interpret. Okay, what a lot of people think is, oh, I'm constructing, I'm going to just jump right into the calculations. That's not the case. These confidence interval questions are actually a lot longer than we think they're going to be. We use what is called the 4-step process. And it is 4 C's. Pretty much every problem the rest of the semester is going to be the 4 C's. The 4 C's are choose, check, calculate, and conclude. So anytime you do any confidence interval at all, you have to do all 4 of these. So that's what I'm going to take you through now. First thing we have to do is say that we are constructing a confidence interval. So we are doing a 90% confidence interval for one proportion using Z. The things that are key here, the 90%, the Z, it's one proportion. Eventually we'll get to two proportions, and it's a confidence interval. I don't really care the order that you put those in, as long as you tell me all of them. I'm doing a confidence interval, I only have one proportion, I'm gonna use Z, and then 90%. And then we have to say what our parameter is. So what we are estimating is we are estimating the population proportion of, and then don't get creative, copy directly out of the question. Proportion of students at this school. So proportion of students at this school that own a graphing calculator. Okay, for the check part, we are checking conditions. And I'm just going to write next page because we're going to do that on the next page in the notes. So we're not going to do that here. But there are 3 conditions that you're going to need to check. And then we are going to calculate that interval. So again, the formula that the formula sheet gives us is statistic plus or minus critical value times the standard error. You don't need to write that down. You just need to be able to put it in symbols. So our statistic is the p hat, a sample proportion. The critical value is Z. So we said proportion's always going to use Z. And then it's going to be the square root. That standard error we saw was p hat, 1 minus p hat all over n. P hat is a sample proportion. So it says they surveyed a random sample of 102 students. 57 of the 102 students own a graphing calculator. So that p hat is 57 out of 102. Can you now look at your formula sheet and find 90%? $1.645. So we get 1.645, and then we have 57 out of 102, 1 subtract 57 out of 102, all over 102. And that interval ends up being 0.478, comma 0.640. And then the last step is the conclusion. You need to conclude, or interpret really, both the interval and the confidence level. I am not going to do that because that's in your notes. So we did that last class. I will get us started. So in terms of the interval, that's what we did in the activity earlier. We are 95% confident. The interval blank to blank, so on and so forth. You would fill that in with context. And then the level we haven't done today except in the warm-up. That's the one that goes, if we took many samples and constructed confidence intervals for each. About 90%. Oh, sorry, this is a 90%, not 95. So I'm going to try to get us through the next page on the quicker side, and then you're going to have an example where you do the full thing. Questions for me? So all we need to do at this point is we're going to talk about the conditions and then a little bit of vocabulary. Okay, next page. At the top, 3 conditions. The first condition will be true for every single confidence interval no matter what. You have to have a random sample. So I remember, you probably don't, it was stated in the question. Second one is we need an approximately normal sampling distribution. Your book calls this large counts. So anytime you see large counts, that's what you're checking. You're checking, do I have an approximately normal sampling distribution? How do we check that for proportion? You just took a test on that. For proportion, how do you check that the sampling distribution is approximately normal? NP greater than or equal to 10, and 1 minus P greater than or equal to 10. Here is the only slight issue. We don't have P. We don't have P, we have P hat. So what you're going to be doing instead is using P hat. Now, you don't need to put the symbols. As long as you put the numbers, that's fine. So we have to use P hat because we don't have P. And then the last rule that we need to check is the 10% rule. And it's the same one that you did before. Generally, we will know little n. So generally what you would do is say big N has to be greater than this, and then you would write a sentence of some type. Okay, so then the natural question comes up. What happens if one of those conditions is violated? So what happens if one is not true? If one is violated, the actual capture rate of the intervals will differ from the advertised rate. Advertised rate in our case being that 90%. Two last things to talk about before you all are going to do an example. Okay, next thing to talk about is there is a difference between standard deviation of a statistic and standard error of a statistic. And this is on the formula sheet. So we have standard error. When it says parameter, there is the standard deviation. So in terms of proportion, the standard deviation of P hat we did before is P1 minus P all over N. But then we just talked about above, we don't have P. We don't have P. So the standard error is the same thing, but with P hat instead of P. So you use P if you have it. If you don't have P, you use P hat. That's pretty much how it goes. And then last thing to talk about before you do an example is the calculator. There is a way to do this on the calculator. I'm not going to show you yet, but I will show you after the next example. Is it okay to use the calculator? Yes, it is. You are going to use the formula and then the calculator to check only. So you will do everything by hand using the formula, but then I'm going to show you how to use the calculator to check your answer. And you might be asking, well, why? That seems like a waste of my time. The reason is that sometimes the multiple choice questions on the AP test use the formula. Similar to, if you remember, binomial. So binomial, I told you don't have to use the formula, but you have to be able to recognize it. Similar idea. You got to be able to recognize the formula for a confidence interval so that you can answer multiple choice questions. Questions for me before you all do an example? Okay, so let's look at this next page. I'm going to get us started, and then you all will do this with the people around you. In her first grade social studies class, Jordan learned that 70% of Earth's surface was covered in water. She wondered if this was really true and asked her dad for help. To investigate, he tossed an inflatable globe to her 50 times, being careful to spin the globe each time. When she caught it, he recorded where her right index finger was pointing. In 50 tosses, her finger was pointing to water 33 times. Construct and interpret a 95% confidence interval for the proportion of Earth's surface that is covered in water. Then, what can you say about the 70% claim? The things I want to point out to you. As soon as it says construct and interpret, that is telling you that you're doing the 4-step process, the 4 C's. So it doesn't say you have to check conditions, but you have to. And then it tells us 50 tosses, her finger was pointing to water 33 times. So our sample proportion in this case is that 33 out of 50. So what I want you to do now is with the person next to you or the group around you, you have until 12:35, 10 minutes. I want the full process, all 4 steps. I'll turn some music on. If you get stuck, let me know. I'll be walking around to help if you need it. Let's start talking about this. Here is my answer. So here's what I'm looking for. In the choose step, that you have 95%, that you have confidence interval, 1 proportion, Z, and then you defined what P is. So what are we estimating? We're estimating the population proportion of the Earth's surface that is covered in water. The conditions are a little bit different. This is not actually a sample. There's not a sample that is happening. There is something that is being performed. So we don't need a random sample, but we need a random process. So in this case, it's random because Jordan's dad spun the globe. To see if we have an approximately normal sampling distribution, you don't need to show this part in symbols. You need to show this part in numbers, and you need to show that both are greater than or equal to 10. You have to show the 10, and you have to show both. And then we've never seen this before where you don't actually have to do the 10% rule. You only have to do the 10% rule when you're sampling. Because remember, we said our formulas are based on the assumption that we're sampling with replacement, which never happens. So we check the 10% rule because then sampling with and without replacement are about the same. Here, no sampling done, don't need the 10% rule then. And here is my calculate step. And the conclusion, we should have 2 different sentences. One for the interval, one for the level. So we are 95%, I worded these differently. So you probably said something like, we are 95% confident that the interval 0.529 to 0.791 contains the population proportion of the Earth's surface that is covered in water. And then for the level, you probably said something like, if we took many, many samples and constructed confidence intervals for each of them, about 95% would contain the population proportion, blah, blah, blah. Did we use either present or future tense? Not past tense? Did we answer the question? The question that was asked is, what can you say about the 70% claim based on the interval? Is it possible that 70% of the Earth's surface is covered in water? Have we proven beyond a doubt that it is? No. So it's possible, but we cannot say that definitively that is true. We got two more things to talk about. Oh, really, one more thing and then an example, and then we're done with notes. I cannot stress enough on your homework, when it says construct, you have to do the entire process. Questions for me before the last thing we're talking about? Okay, do you remember when we did the activity the other day where I said when we talked about why you wouldn't just choose the biggest margin of error possible? We said sometimes if your margin of error is too big, it gives you an interval that's not helpful because it ranges too many values. Okay, so a lot of times what will happen is statisticians will want to know what sample size they need to choose in order to keep the margin of error so big. Like they want a margin of error of 0.1. How can they do that? So when solving for the second question, we're going to skip the first one. When solving for sample size, how do you use a value of p hat? Because you're doing this before you've carried out the study, so you don't have p hat, but you need it for standard deviation. Three options. You can use a previous value. Like historically, this was believed, blah, blah, blah. If you don't have a previous value, you can use a value from a pilot study, like a TV pilot, for example. And then lastly, if neither of those is an option, you just use 0.5. 0.5 would be a conservative estimate. It would give you the largest possible sample that you needed. So here's our example. Suppose that you wanted to estimate P, which is the true proportion of students at your school who have a tattoo with 98% confidence and a margin of error of no more than 0.1. How many students should you survey? Okay, 98% confidence, margin of error of 0.1. So 0.1 is our margin of error. The actual way we calculate margin of error is z, the square root of p hat, 1 minus p hat, all over n. So this is what we have to fill in. That z, like we've been doing, you find on the table. I will tell you it's 2.326. P hat is a sample proportion. That is not 0.1. 0.1 is the margin of error. Sample proportion we don't have. So if you don't have it, you're going to use 0.5. And then n is what we are choosing, or what we're solving for. How many students should you survey? That's n. This is what we need to solve. Okay, so what I'm going to do is I'm going to divide by 2.326. And then I'm going to end up squaring everything to get rid of that square root. So we'll have 0.1 over 2.326, all of that squared. And then I have 0.25 over n. So I'm just doing a few steps at once. Ultimately, what we're going to end up doing is if we're dividing by n, we're going to have to multiply it to the other side. And we'll have to divide by this quantity. So where we'll end up with next then is we'll end up with n is greater than or equal to 0.25 divided by that entire squared quantity. So if you trust me that I think I rounded a little bit, I got 135.7. It is essential that you show that decimal. This is the only time in stats that you're going to round. Because practically we cannot take a sample size of 135.7. You will always round up no matter what. So 136 is the smallest possible sample to keep a margin of error of 0.1. Lucy?
If it was like 135.2, would you still round up to 136? Okay.
Great question. It's 135.2, you're still rounding to 136.